Hello all, I will be presenting my term project of CHN-302 on the topic Sustainable Housing Colonies here with the focus on heat transfer modeling of cool roofs and its implementation. We notice that in hotter countries, due to higher temperatures, there is a significant increase in temperature inside the houses, causing a significant discomfort, energy losses, and economic losses. To tackle this problem, we are undergoing modeling and simulations under COMSOL multi-physics simulation software to understand the concept of cool roof better by analyzing effectiveness of different materials, roof geometries, and other external factors like humidity and natural convection. So after this, let's move on to our COMSOL multi-physics software. We will see the simulation here. So at the first, for our modeling approach, we'll start with creating the geometry. Here we have taken the basic cubic geometry for the room demonstration and making all the other layers. So here we have taken one by one meter basic room, and after that we have taken the above layers with 5 centimeter thickness and the 1 centimeter thickness of the uppermost layer, which is our full roof. And we formed its union to make it as a whole one system. After that, we have taken different materials and allocated them to the different layers. We have aluminium as the layer of our cool roof. We have air, which is filled up in our room, as we can see. We have cellular concrete in our walls, you can see here, and we have white pottery clay in this middle layer. After that, we use the heat transfer in solids physics, in which we have taken this our whole solid as our system. We have taken initial value temperature as 293.15 as the room temperature. We have taken sufficient insulations wherever the heat flux is not there. We have taken heat flux as 1500 watt per meter square on the above of the roof, and we have taken a heat flux, second heat flux of 300 on the walls of this room. So here we have taken 300 because on the side walls and on the windows we get an average of lesser solar radiations as an average. So moving forward on the mesh, we have taken a normal meshing as the subdomains for the solver settings, and then we are doing the time dependent study and using its equation to solve this. After this simulation running an ample of time, we get the temperature results as follows. For each and every x, y, z, we can get the values in this table here. We have studying this at a steady state at 10,000 seconds. We can also see the isothermal contours here and various other plots here in the software. So getting back to the presentation, in our modeling approach moving forward, we can quickly see that we use this geometry, we use this white pottery clay, aluminium, air, and silicon concrete as our materials for different layers. We have used heat transferring solids as our physics. We have used these equations as I already mentioned in this simulation. We have used the basic normal meshing with these element qualities and values here. After that, let's jump on to our results and conclusions. So here we are judging on different material effectiveness. So firstly, we are using a traditional concrete roof, which is in our day-to-day life. In that, for a thickness of 10 centimeter and basic block geometry, we can see the different values of temperatures here at different x, y, z. So at the bottom of this roof, at we are considering it as room temperature, we get it as 297.333 Kelvin, which is quite high. And in the second part, now we can see for the wood pine roof with the same thicknesses and geometry of for all six materials, we get the minimum temperature similarly as 295.34 Kelvin. For the steel roof, we get it significantly well. It shows that it's a good material for the cool roof, 293.21 Kelvin at the bottom of the roof. Moving forward to the aluminum roof, again a metal performed really well, 293.28 Kelvin at the minimum temperature. After running the simulations, you can see in these diagrams. The granite roof, 294.4, not bad. And white pottery clay roof performed as 294.34 Kelvin at the bottom temperature. Now you can see the comprehensive comparison here as the materials performed really better than the concrete, which is a traditional layering material. We can see that metals performed really well and white pottery, clay, granite, and wood performed decent. Now moving to the geometry, we also judged them on the basis of geometry. We have used the flat roof, we have used pyramid roof, and our complex geometry, which I showed in the previous console software. So here we got the minimum temperature at the bottom as 293.5. Here we got in the pyramid simulation, we got it as 293.45 Kelvin here, as we can see, with the height as 15 centimeter for the pyramid, keeping the volume same in each case. And then for the multi-layered and different materials, we got the minimum roof temperature as 293.70 Kelvin. Moving forward, for the variation of temperature with thickness, at the steady state with cubic geometry and white pottery clay material, we get to see that as the thickness increases, the temperature decreases. In the last objective, we see that effect of humidity, wind speed, and natural convection with wind speed as 20, LS 3 meter, and relative humidity as 0.45. You can see the temperature difference without effects and with effects in these simulations. So we can see the difference here. Thank you very much.